Hey everyone, welcome to our next lesson in our unit on modern physics. Today's lesson is going to be on early models of the atom, which most of you at this point would have some experience with, having taken chemistry prior to taking physics. So we'll take a look at how some of the early models of the atom led to some later discoveries, which have influenced our understanding of subatomic particles in the atom and some of the behaviors that we see not only on the micro level or the atomic level, but also the macro level as well. So to start here, we know that from your experience in chemistry, that an atom is the smallest particle of an element that retains the characteristics of the element. We know that there's smaller subatomic particles that make up the atom, but the individual atom will still have all of the properties and characteristics of, let's say, the elements gold or mercury or silver, something like that. Once we start taking away protons, neutrons, or electrons, then we start changing what the atom actually is, and therefore its behavior properties. Now, these models have changed over time, really because the technology that has been used to study them and develop these experiments has changed over time as well, which has allowed some different experiments to occur as we've had greater technology to help increase our understanding of this very unknown particle of matter, the atom. So one of the earlier models that we'll talk about is the Thomson model. You might remember this as the plum pudding model. And really, Thomson discovered that electrons are very low mass and that they have a negative charge. And this is kind of one of the first times that we've come to understand that electrons are an actual particle and that they have negative charge. Now, Thomson also thought that the atom had a uniform distribution of positive charge equal to the total negative charge from the nucleus. Now, the second part of that is right. In a neutral atom, we have positive charge equal to negative charge, but it's not uniformly distributed like he described in his plum pudding model. But at the time, with the technology available, that's the best description that he could provide, which given the time was pretty good. The later models are going to come to expand on that and realize that the positive charge is not uniform throughout the atom, and nor is the negative charge. And we started to discover that with Ernest Rutherford's model, which he developed by performing, if you remember this, the gold foil experiment, where he took a small number of particles, positively charged alpha particles, and directed them in a dense beam at a thin sheet of gold foil. And he expected most of these to kind of just move straight through or get deflected, maybe a little bit from some of the Coulomb forces in there, but they weren't. There were a small number of particles that were scattered or deflected at really large angles. So that kind of led him to conclude that the concentration of mass, and therefore positive charge, because he was directing positively charged alpha particles towards the foil. So he concluded that the concentration of mass and positive charge is located in the nucleus. And this directly contradicted what Thomson had thought. And we refer to this oftentimes as the solar system model, which kind of helps show that we have a dense concentration of mass at the center of the solar system, like a sun or the nucleus, which contains, as I said, most of the mass. And then we have all the positive charge is surrounded by negatively charged electrons or planets that are moving in these specific orbits around the nucleus. And this served as a pretty good understanding for a little while, but it couldn't quite explain the appearance of spectral lines of different elements. So Bohr comes along and improves on Rutherford's model. And Bohr tried to explain why electrons maintain positions outside the nucleus rather than spiral into the nucleus. If you think about a negatively charged electron moving around a positively charged nucleus, why don't they just kind of attract to each other and the electrons can attract to the nucleus and kind of stay there? So he tried to explain why that is not happening. So he developed a model of the hydrogen atom based on a few different assumptions. And he said that all forms of energy are quantized, meaning electrons can only gain or lose energy in fixed amounts or quanta. We learned about this last lesson. This energy known as packets. It's a specific amount of energy. So that the electron in the hydrogen atom can only occupy specific orbits. It can't just go wherever it wants. So it's going to occupy a specific orbit of fixed radius and no others. Electrons can move or jump up energy levels by absorbing a specific quantum of energy, which would have to come in the form of a photon. And each orbit corresponds to a specific amount of energy, where the orbit that is going to be nearest to the nucleus represents the smallest or most negative value of energy that the electron can have. And energy is going to increase in orbits as we move farther away from the nucleus. And that's indicated in your reference table. Now, any electron in any particular orbit is said to be in what we call a stationary state. The electron's stationary, it's staying in that particular level. And each stationary state is going to represent a specific amount of energy, and that is called the energy level. Now, electrons in the lowest energy level are called the ground state. And when electrons are in any other level greater than n equals 1, indicating the first state closest to the nucleus, then the electron is in the excited state. Now, we can excite electrons in a few different ways, but ultimately, exciting electrons can result from absorbing energy from other particles of matter that are colliding with the atom or with the electron. And this can be forms of matter like electrons, or it could be by photons. And this is where our wave-particle duality of energy and matter comes into play. Now, the photon's energy is only absorbed if its energy corresponds exactly to an energy level for the electron. And these energies are going to be different for each element based off of their varying electron configurations. Now, as electrons return to the ground state, they lose energy, and that energy is going to be lost or emitted in the form of photons of specific frequencies, which are going to appear as spectral lines for that particular element. Now, these photons, these are any form of electromagnetic radiation. Oftentimes, if we look at the ones in the visible spectrum, those are the ones we can see, but we oftentimes have atoms that are emitting photons that are going to be in the ultraviolet or infrared regions, which we're not able to see with our eyes. Now, if an atom can absorb sufficient energy, instead of maybe jumping 1 level, 2 level, 3 levels, the electron can actually be removed from the atom, and that's how we form an ion. The energy that's required to do this, to completely remove the electron from the atom, is called the atom's ionization potential. We learn this in chemistry as the ionization energy. Now, the energy level diagram which we see below, is one in which the energy levels of a quantized system, in this case is the energy levels for a hydrogen atom, they're indicated by horizontal distances from a 0 energy level. And that is right on top there. And as we go down towards the ground state, we see that our energy is getting smaller or more negative, where our energy level n equals 1 is going to be our lowest energy, indicated by the most negative value. So essentially, to remove an electron in the first state of a hydrogen atom, we'd have to remove, or the electron would have to absorb 13.6 electron volts of energy. Now, the most current model that we're generally following in the field of chemistry and physics is the cloud model. And with all of our advanced technology, this is the best model that we can come up with at this time. Not to mean that it won't change in the future with changing results from experiments and technology, but this is the best one that we can follow at this point. And in this model, electrons are not going to be confined to specific orbits as we thought in the Bohr model. It's not a perfect planetary layout. Electrons are going to be spread out in a space which we call the electron cloud. Now, the cloud is going to be densest, which we see right in the middle here, the darker color indicating a denser region where the likelihood of finding an electron is the greatest. We can still find an electron out here, but the likelihood of that is extremely small. And it's much, much, much greater to find one in the middle of the densest part of the cloud. Now, different complicated equations can describe the shape, location, and density of each electron cloud. And there are some different classes in different fields of chemistry and physics that you can get into that explore those different shapes, which we can see some of these hybrid orbitals outlined here. And these equations attempt to explain why the cloud forms the way it does, which therefore will indicate likely or unlikely areas to find electrons. Now, atomic spectra, we looked at these during chemistry using spectroscopes and gas discharge tubes. And we used those discharge tubes and excited the gas inside, the atoms of the gas inside, using electricity. And when the electrons in those particular elements return to the lower energy levels, they produce a series of frequencies of electromagnetic radiation called the atomic spectrum of the element. Now, each element has its own characteristic spectrum that differs from every other element. So we can use this property to identify elements in an unknown sample. because each element's going to give off its own specific or unique or characteristic spectrum that can be used to identify from any other element. Now, when an electron in an excited state falls to a lower energy level, the energy of the emitted photon is going to be equal to the difference between the energies of the initial and final states of the electron, and it's represented by the equation here. So the energy of the emitted photon is equal to the change in the initial energy of the electron and the final energy of the electron. And that's going to correspond to a specific type of photon. For example, if we have electrons that are shifting from, we'll look at this first bracket series here, shifting from a energy level of n equals 7 down to 4, from 6 to 4, 5 to 4, this energy change will produce a photon in the infrared region. The Paschen series and the Balmer series, where we have a little bit of a farther drop, these are going to be a larger amount of energy, from 7 to 2, or really anything from a higher level to 3 or down to 2. These are going to produce photons in the visible light region. Now the Lyman series, where we have drops from 7 all the way down to 1, or really any drop down to the lowest energy level here, this is going to produce photons in the ultraviolet region, which we can't see. We're only going to see these transitions here in the Paschen and the Balmer series, where they're emitting photons in the visible light region. Now, when these frequencies are viewed through a spectroscope, all these photons that are being emitted, if we look at them through a spectroscope, the frequencies appear as a series of bright lines against a dark background, which we call a bright line spectrum or an emission spectrum. And it's called an emission spectrum, and that's why I want to define this here, because these are photons that are being emitted. And it's important to note that because if we expose an element to white light, which contains all the frequencies of visible light, the atom's going to selectively absorb the exact frequencies it would emit when excited. And these are going to appear as dark lines against a full white light background, and we call that the element's absorption spectrum. That's essentially the opposite of what an emission spectrum or bright line spectrum is. So for example, we have two different spectra for hydrogen here. And we have a hydrogen alpha line at 656 nanometers, and that's a result of a transition from n equals 3 to n equals 2. Now this would be a emission. As we're going down in energy level, we're emitting a 656 nanometer photon. Now, if we go from N2 to N3, we have to absorb a certain amount of energy, and that absorption is going to be the exact same photon for that transition in the case of hydrogen. So if we combine these two, what we get is the full white light spectrum. And if we look at an emission spectrum, the negative of the emission spectrum is the absorption spectrum. We can see each of these lines line up with each other, one indicating when the electrons are absorbing energy to jump and move, and one indicating when electrons are emitting photons as they drop down to their original energy levels. If you guys have any questions on this, make sure you write them down and see me to get your questions answered. Hope everyone has a wonderful day.